Hello all, welcome to this video on machine learning. Today I'll be talking about multi-layer feed-forward network and activation function. Now, a multi-layer feed-forward network is also known as a feed-forward neural network or a multi-layer perceptron. The goal of a feed-forward network is to approximate some function which is given by f star. For example, for a classifier y is equal to f star of x, maps an input x to a category y. A feed-forward network defines a mapping y is equal to f of x, theta, and learns the value of the parameters theta that result in the best function approximation. These models are called feed-forward networks because information flows through the function being evaluated from x, through the intermediate computations used to define f, and finally to the output y. There are no feedback connections in which outputs of the model are fed back into itself. When feed-forward neural networks are extended to include feedback connections, they are called recurrent neural networks. Neural networks investigate how simple models of biological brains can be used to solve difficult computational tasks like the predictive modeling tasks we usually see in machine learning. Mathematically, they are capable of learning any mapping function and have been proven to be a universal approximation algorithm. The predictive capability of neural networks comes from the hierarchical or multi-layered structure of the networks. The data structure can pick out features at different scales or resolutions and combine them into higher order features. For example, from lines to collection of lines to shapes. Now, the building block of neural networks are artificial neurons. These are simple computational units that have weighted input signals and produce an output signal using an activation function. Each neuron has a bias which can be thought of as an input that always has a value 1.0 and it must be weighted. Weights are often initialized to small random variables such as values in the range 0 to 0.3. The image here shows how a multi-layer neural network identified different objects by learning different characteristics of the object at each layer. For example, from the bottom, at the first hidden layer, the edges are detected. On second hidden layer, corners and contours are identified. Similarly, there are different regions in our brain which are there for the same purpose, as we can see the region which is denoted in red as V1 that identify the edges, corners and etc. By applying neural network, we can overcome the problem of non-linearity. In the figure on the left, the neural network has trained a model by combining different distributions in one desirable distribution, considering the non-linearity of the problem. So the figure depicts the different neurons in the hidden layer by combining different distribution and come up with a new combined desired distribution. Neural networks emerged from a very popular machine learning algorithm named as perceptron. Perceptrons were developed in the 1950s and 1960s by the scientist Frank Rosenblatt, inspired by earlier work by Warren McCulloch and Walter Pitts. The figure here shows a perceptron layer. Suppose we have a network of perceptrons to solve some problem. For example, the inputs to the network might be the raw pixel data from a scanned handwritten image of a digit. And we would like the network to learn the weights and bias so that the output from the network correctly classifies the digit. To see how the learning might work, suppose we made a small change in some weight or bias in the network. What we would like is for this small change in weight to cause only a small corresponding change in the output from the network. But we'll see that this property will make learning possible. But as it occurs, a small change in weight can lead to big change in output. So using a neuron model like sigmoid can solve this issue. Let us see how. The figure here depicts the behavior of a sigmoid function. Unlike piecewise linear units, the sigmoidal units saturate across most of their domain. That is, they saturate to a high value when z is very positive, saturate to a low value when z is very negative, and are only strongly sensitive to their input when z is near 0. This property of sigmoid function solves our problem. Now we look into the architecture of neural networks. The leftmost layer in this network is called the input layer, and the neurons within the layer are called input neurons. The rightmost or output layer contains the output neurons, or as in this case, a single output neuron. The middle layer is called a hidden layer, since the neurons in this layer are neither inputs nor outputs. In the figure, VIL notation is used to denote the weight of the ith neuron of lth layer. Wi, j, L denote the weight for the connection from the jth neuron in the L-1th layer to the ith neuron in the lth layer. We'll use Bi for the bias of the ith neuron and h of x for the activation function. F of x here will be the output function. As we already saw, this model provides a universal approximation framework. To be specific, the universal approximation theorem says that there exists a network large enough to activate any degree of accuracy we desire, but the theorem does not say how large this network will be. Let us see how this works by taking an example. The figure here illustrates how a network with absolute value rectification create mirror images of the function computed on top of some hidden unit with respect to the input of that hidden unit. Each hidden unit specifies where to fold the image space in order to create the mirror response on both sides of the absolute value non-linearity. By composing these folding operations, we obtain an exponentially large number of piecewise linear regions which can capture all kinds of regular, that is, repeating patterns. Now the left image, an absolute value rectification unit has the same output for every pair of mirror points in its input. The mirror axis of symmetry is given by the hyperplane, which is defined by the weights and bias of the unit given by the dotted lines. A function computed on top of that unit, which is given by the green decision surface, will be a mirror image of the similar pattern across that axis of symmetry. The center image now. The function can be obtained by folding the space around the axis of symmetry. Now going to the right-hand image. Another repeating pattern can be folded on top of the first, that is by another downstream unit, to obtain another symmetry which is now repeated 4 times with 2 hidden layers. Once a neural network is configured, it needs to be trained with the data set. Now before training, the data needs to be prepared. Data must be numerical, for example, real values. If we have categorical data, such as a sex attribute with the values male and female, we can convert it to a real valued representation called a one-hot encoding. This is where one new column is added for each class value, the 2 columns in this case of sex of males and females. And a 1 or 0 is added for each row depending on the class value for that row. The same one-hot coding can be used on the output variable in a classification problem which has more than one class. This would create a binary vector from a single column that would be easy to directly compare to the output of the neuron in the network's output layer, which would output one value for each class. Neural networks require the input to be scaled in a consistent way. We can rescale it to the range between 0 and 1. This is called normalization. Another popular technique is to standardize it so that the distribution of each column has a mean of 0 and a standard deviation of 1. Scaling also applies to image pixel data. Data such as words can be converted into integers, such as the popularity rank of the word in the dataset and other encoding techniques. Designing and training a neural network is not much different from training any other machine learning model with gradient descent. The largest difference between the linear models we have already seen and neural networks is that the non-linearity of a neural network causes most interesting loss functions to become non-convex. This means that neural networks are usually trained by using iterative, gradient-based optimizers that merely drive the cost function to a very low value rather than the linear equation solvers that are used to train linear regression models or the convex optimization algorithms with global convergence guarantees used to train logistic regression or SVMs. Now let us look into activation function. Activation functions in general are used to convert linear outputs of a neuron into non-linear outputs, ensuring that a neural network can learn non-linear behavior. In the network given here, each neuron is composed of weights vector and a bias value. When a new vector is input, it computes the dot product between the weights and the input vector, adds the bias value, and outputs a scalar value. Both the dot product and scalar additions are linear operations. Hence, when you have this value as neuron output and do this for every neuron, we have a system that behaves linearly. As we already know, most data are highly nonlinear. Since linear neural networks would not be capable of generating a decision boundary in such cases, there would be no point in applying them when generating predictive models. For this purpose, we will be using an activation function. Now this function, which is placed directly behind every neuron, takes as input the linear neuron output and generate a non-linear output based on it, often deterministically. That is, when you input the same value twice, you will get the same result. This way, with every neuron generating an effect, a linear but non-linear output, the system behaves non-linearly as well, and by consequence becomes capable of handling non-linear data. Now we'll look into different activation function. The first is a sigmoid function. Sigmoid function is also known as logistic curve, which looks like as given in the figure. Mathematically, it can be represented as y giving f of x is equal to 1 by 1 plus e raised to minus x. As we can see in the plot, the function slowly increases over time, but the greatest increase can be found around x is equal to 0. The range of the function is 0, 1 without including 0 and 1. That is, towards high values of x, the function approaches 1 but never equals it. We use a sigmoid function because it outputs between 0 and 1. When estimating a probability, this is perfect because probabilities have a very similar range of 0 to 1, including both 0 and 1. Especially in binary classification problems, when we effectively estimate the probability that the output is of some class, sigmoid functions allow us to give a very weighted estimate. The output, for example, if is 0.623 between classes A and B, this would indicate that slightly more of B. Now with a step function, the output would have likely been 1. and the nuance disappears. Now we look into hyperbolic tangent function or tanh function. Now this works similar to the sigmoid function, but it has some differences. The curve is shown in the figure. First, the change in output accelerates close to x is equal to 0, which is similar to the sigmoid function. It also shares its asymptotic properties with sigmoid. Although for very large values of x, the function approaches 1, it never actually equals it. On the lower side of the domain, however, we see a difference in the range. Rather than approaching 0 as minimum value, it approaches minus 1. Now we'll see the differences between sigmoid and hyperbolic tangent function. Obviously, the range of the activation function, as we already saw, which is 0, 1 without including 0 and 1 for sigmoid versus minus 1, 1 without including minus 1 and 1 for hyperbolic tangent function. Although this difference seems to be very small, it might have a large effect on model performance, specifically how fast the model converges towards the most optimal solution. The outputs that are close to 0 are best during optimization. They produce the least weight swings and hence let the model converge faster. This will be helpful when the models are very large indeed. Also, we see that the tanh function is symmetric around the origin, whereas the sigmoid function is not. Now we'll see some challenges of sigmoid and hyperbolic tangent function. The first is model sparsity. The less complex the model is during optimization, the faster it will converge and more likely it is that we'll find a mathematical optimum in time. Complexity can be viewed as the number of unimportant neurons that are still in the model. The fewer, the better or sparser the model is. Sigmoid and tanh essentially produce non-sparse models because their neurons pretty much always produce an output value that is in the ranges of 0, 1 without including 0 and 1 for sigmoid, and the range minus 1, 1 without including minus 1 and 1 for tanh respectively. The output either cannot be 0 or is 0 with very low probability. Hence, if certain neurons are less important in terms of their weights, they cannot be removed and the model is not sparse. Another possible issue with the output ranges of the activation functions here is the vanishing gradients problem. During optimization, data is fed through the model, after which the outcomes are compared with the actual target values. This produces what is known as the loss. Since the loss can be considered to be an optimizable mathematical function, we can compute the gradient towards the zero derivative, that is the mathematical optimum. Neural networks, however, comprise many layers of neurons. We have to repeat this process over and over again for every layer with respect to the downstream ones and subsequently change them. We can optimize our models with gradient descent or a similar optimizer. When the neuron outputs are very small, that is in the range of minus 1 to 1, the chains produced during optimization will get smaller and smaller towards the upstream layers. This will cause them to learn very slowly and make it questionable whether they will converge to their optimum at all. In order to improve on these observations, another activation function was introduced, which is the Rectified Linear Unit Function or ReLU, which is the first choice for most deep learning projects today. It is much less sensitive to the problems mentioned above and hence improves the training process. It looks as shown in the figure. which is represented mathematically as f of x giving 0 when x is less than 0 and x otherwise. That is, it produces a 0 output for all inputs smaller than 0 and x for all other inputs. Hence, for all inputs less than or equal to 0, it produces 0 outputs. This function benefits sparsity substantially. In almost half the cases, now the neuron doesn't fire anymore. This way, neurons can be made silent if they are not too important anymore in terms of their contribution to the model's predictive power. This function also reduces the impact of vanishing gradients. Because the gradient is always a constant, the derivative of f of x equal to 0 is 0, while the derivative of f of x equal to x is 1. Models hence learn faster and more evenly. Additionally, this function does need much fewer computational resources than sigmoid and tanh functions. This function essentially needs to be executed as max of 0x, which is a max function, which produces 0 when x is less than 0 and x when x is greater than or equal to 0. Now comparing this with the formulas for sigmoid and tanh functions, which contain exponents, computing the output of a max function is much simpler and less computationally expensive. But this function also has certain challenges. Firstly, it tends to produce very large values given its non-boundness on the upside of the domain. Theoretically, infinite inputs produce infinite outputs. The second is the problem of dying ReLU problem. That is, if a neuron's weights are moved towards the 0 output, it may be the case that they eventually will no longer be capable of recovering from this. They will then continually output zeros. This is especially the case when the network is poorly initialized or when the data is poorly normalized, because the first rounds of optimization will produce large weight swings. When too many neurons output 0, we end up with a dead neural network. Thirdly, small values, even the non-positive ones, may be of value. They can help capture patterns of the underlying dataset. But with this function, this is not possible since all outputs smaller than 0 are 0. Fourthly, the transition point from f of x equal to 0 to f of x equal to x is not smooth. This will impact the loss landscape during optimization, which will not be smooth either. This may hamper the model optimization and slightly slow down the convergence. That's all for now. Thank you for watching.